everybody. Firstly, I wish you Happy Pi Day. In the square of celebrating the International Day of Mathematics, we are honored and happy to present a work entitled Mathematical Modeling of Cancer Dynamic System, which is done by myself, Lulu Samah, and my colleague Maysa Basir, under the guidance of Dr. Debush Ammar. We will start to talk about a short introduction of cancer dynamics. Human cancer is a multi-step process involving acquired genetic mutation, each of which impart a particular type of growth advantage to the cell and ultimately leads to the development of a multigauge phenotype. يعني سرطان الإنسان هو عملية متعددة الخطوات تتضمن طفرات جينية مكتسبة تؤدي في النهاية إلى تطور النمط الظاهري الخبيث. It is also a generic term of a group of diseases and figures as a leading cause of death globally. It lays a significant burden on healthcare systems and continues to be among the major health problems worldwide. وهو أيضا مصطلح عام لمجموعة من الأمراض والأرقام كسبب رئيسي للوفاة على مستوى العالم ككل. وهو من بين المشكلات الصحية الرئيسية في جميع أنحاء العالم. The consequence of mutation in tumor cells include alteration in cell signaling pathways that result in uncontrolled cellular proliferation, insensitivity to growth inhibitory signals, resistance to apoptosis, development of cellular immortality, angiogenesis, tissue invasion, and metastasis. عواقب الطفرات في الخلايا السرطانية تؤدي إلى تكاثر خلوي غير متحكم فيه، عدم حساسية لإشارات تثبيط النمو، مقاومة موت الخلايا المبرمج، تطوير الخلود الخلوي، تولد أوعية وغزو أنسجة. The current treatments still present substantial limitation, do not fully restore health, and the offered medication are not curative. لا تزال العلاجات الحالية تفرض قيودا والأدوية المقدمة ليست علاجية. In fact, there is no cure or vaccine to the above deadly diseases, but medication can dramatically slow the progression of the diseases. في الواقع لا يوجد علاج أو لقاح لهذه الأمراض المذكورة أعلاه، لكن الأدوية يمكن أن تبطئ بشكل كبير من تطور المرض. So, this serious problem motivated us to investigate this controversial subject. دفعتنا هذه المشكلة الخطيرة للتحقيق في هذا الموضوع المثير للجدل. We would like to model the previous danger diseases mathematically as follows. Consider the dynamics of cancer invasion system with time fractional and non-local division 1-1. With the following initial and boundary condition. Where Qt and sigma t are defined for some t positive, which is final time, and alpha in 0-1, here omega is a bounded domain in Rn with smooth boundary. The unknown function u1 and u2 respectively describe the density of two types of cancer cells. Further, U3 and U4 respectively represent the density of normal cells and medium acidification concentration due to excess H plus ions. The constants beta 1 and beta 2 respectively denoted the rates of interaction, and the positive constant rho delineates the intrinsic mutation rate of cancer cells. Furthermore, gamma 1 and delta 1 represent the rate of consumption of cancer cell population. The proliferation rate of cancer cells is given by R2 and R3 are positive. Here Xi represents the product rate of the H plus ions. Moreover, gamma 2 and delta 2 respectively denoted the interaction rate of two types of cancer cells with normal cells, and sigma denotes the degradation rate of normal cells due to acidification. In system 1-1, the diffusion rates di from R to R are the Lipschitz continuous function, with di more than or equals mi is positive. Further, di are taken to be depend on the wall of each population in the domain rather than on the local density, and the linear continuous non-local operator Ls in L2 prime, where S is a real number. Now we are in position to study the existence and uniqueness of weak solution for cancer invasion system 1-1. Our main tool is to use the Fido-Galerkin approximation method and deriving uniform a priori estimate for approximation of solution. For that, we review some auxiliary results. We start by theorem 1-1. Consider the fractional ordinary differential equation 2-1 as it is well known if f a continuous function satisfying the Lipschitz condition, then 2-1 has a unique solution. Lemma 2-1, suppose you define as follow, and its fractional derivative exists, then the following inequality is satisfied. Lemma 2-2. Let alpha in 0-1 and a non-negative integrable function C1 for t in 0t satisfy the inequality 2-2 for almost all t in 0t, then the inequality 2-3 holds. Lemma 2-3. Let alpha in 0a, suppose u, v are two integrable functions, v is non-decreasing and g is a continuous function in AB. If the following inequality holds, then the next one is satisfied, where alpha is one parameter Mittag-Leffler function. Lemma 2-4. For alpha in 0-1, suppose u is a non-negative absolute continuous function on 0t, which satisfies for almost everywhere t the following differential inequality 2-4 for constant c positive, then this inequality for the proof, we use lemma 2-2 and lemma 2-3, we get our results. Assume that X is in Hilbert space and we define the Fourier transform, we get our results. Theorem 2-2. Assume that this mapping is continuous and the next one is compact. So the following one is compact. We rewrite system 1-1 as system 2-5, where G1, G2, G3 are given. Theorem 2-3. Suppose the initial conditions in L2, then the system 2,5 admits weak solution, which satisfies the following conditions. Now we use the following regularized system in order to find weak solution of the system 2,5 with the following initial and boundary condition. We apply the Fido-Galerkin method to solve 2,7. We get our solutions. Thus, we get the system 2,9 from theorem 2,1. There is the existence of solutions. Lemma 2,5 assume the hypothesis of theorem 2,3. Then the inequality 2,10 is holds. Lemma 2,3 assume the hypothesis of theorem 2,3. Then such that the tilde is defined as follows. Suppose the hypothesis of theorem 2,3 holds true, then the regularized system 2,7 possesses a weak solution which satisfies the following conditions. For proof, we use lemma 2,5, 2,6 and theorem 2,2. We get the following convergence in weak and weak sparseness. Lemma 2,3 assume that the assumption of theorem 2,3 are satisfied, then 2,5 holds. From the theorem, we use lemma 2,5 and our assumption. Lemma 2,8 assume the hypothesis of theorem 2,3 are held true, then this vector is bounded set on this space, such that the tilde are defined as follows. For the proof is similar as proof of lemma 2,6. For proof of theorem 2,3, we use lemma 2,7, 2,8 and theorem 2,2. We get this convergence. Now we show the uniqueness of weak solution. We use classical method, assume that our problem has two solutions. Then we make this different. We use Lipschitz assumption and with unique inequality and lemma 2,3 we get this inequality. It is easy to check the right hand side tends to 0, hence we have the uniqueness of solution. Then my college will contain the speech. Thank you.
Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. Hello everybody, welcome again. Now I will continue our speech, so let me talk about finite element chain. In this section we present finite element chain for the considered model 1.1. Here first we present a weak formulation for time fractional constant in Bayesian system 1.1, where the time fractional derivative is the capital derivative. Further, the spatial and temporal discretization are presented. Furthermore, an iteration fixed point type is proposed to handle the nonlinear terms of the system. The first subsection of this part is finite element semi-discretization. Let the H be a partition of omega into non-overlapping triangulars Pk belongs to H cells, and use the piecewise linear P1. Finite elements on each cell. Now let VH belongs V be a conforming finite element subspace of V with basis function phi k, where capital N is the number of degrees of freedom. Then the semi-discrete problem based on 2,6 is to find solution such that for any almost everywhere T and for all psi 3,1 is satisfied, where V and F are given as follows. Using this basis, we describe the discrete solution in terms of the basis of VH as follows. Thus, we have equation 3,2 such that all its terms are given explicitly as follows. The system 3,2 is fractional ordinary differential equation system. Solvability of system 3,2 can be achieved as in theorem 2.3 and theorem 2.5. The second subsection of this part is temporal discretization and linearization. We present now the time discretization of 3,2. Let this partition be decomposition of the considered time interval 0t. We discretize the copy to fractional time derivative by using finite difference shear. This approximation is given by 3.5. Substitute 3.5 in 3.1, we have 3.6. Moreover, we used fixed point iteration technique to control the nonlinear terms of the given system. In addition, we iterate until the residual is less than the prescribed threshold value 10 minus 10 or the given maximal number of iterations is reached. In computations, the fixed point iteration converges within 6 or 7 iterations for the prescribed residual value. Furthermore, the number of fixed point iteration increases when delta t is increased. The fourth section of this work is numerical experiment. In this section, we perform a series of numerical computations to understand the impact of alpha in constant invasion system. Here, all numerical computations are performed in the unit square domain omega. We use time notions in biology for the convergence study. We consider the constant invasion model to 5 by 4.1, where FU1, T, FU4 are forcing terms. The IR shows such that the following smooth solutions are satisfied for 1. Moreover, we fix diffusion and use the below values. A set of finite element computations are uniformly defined meshes with delta t are performed. In order to compare the discretization errors at different mesh levels and verify the order of convergence of numerical shear, the following errors are computed for each announced UG. First, for alpha equals 0.4, then the obtained numerical errors and corresponding convergence rates are depicted in table 1. For alpha equals 0.7, obtained results are shown in table 2. Table 1 and 2 clearly shows that existence of second order convergence for the errors E1 and E2 respectively for all announced of the system. As we said, table 1 shows errors and order of convergence when alpha equals 0.4. Also, we have table 2 that shows errors and order of convergence when alpha equals 0.7. We have also the following simulation which shows evaluation of U1 and U2 at t equals 10 and 20 with different values of alpha. Also, figure 2 represented evaluation of U3 and U4 at t equals 10 and 20 with different values of alpha. Figure 3 showed evaluation of U1, U2, U3 and U4 at t equals 5 along the line y equals x. Figure 4 shows evaluation of U1 till U4 at t equals 10 along the line y equals x. Figure 3 represented evaluation of U1 till U4 at t equals 15 along the line y equals x. The last figure shows evaluation of U1, U2, U3 and U4 at t equals 20 along the line y equals x. The second subsection of this part is numerical results and discussion. We understand the influence of fractional derivative on constant invasion system 1.1 by performing numerical simulations with different values of alpha. All computations are performed at time t equals 20. Further, uniform time step size delta t is taken as 0.1. We discretize the unit square domain using triangular elements with characteristic element with this length. And a uniform mesh size, we use these degrees of freedom for each unknown in all computations with total these degrees of freedom. We assume the homogeneous directly boundary conditions for all unknowns with the following initial conditions, where epsilon1 and epsilon2 are given as follows. We performed simulations for different values of alpha, and all other parameters are taken of the model of the previous section. Now numerical simulations are carried out to analyze the influence of fractional parameter alpha on the constant invasion system to 5. The first two rows of figure 1 show the comparison between the fractional derivative alpha when alpha equals 0.1 and 0.7, and the integer order derivative of constant density u1 at time t equals 10 and 20. Similarly, rows 3 and 4 of figure 1 show the effects of constant density u2 at time t equals 10 and 20. Differences on the evolution of u1 and u2 can be observed depending on the value of alpha. We observed huge morphological changes in the invasion of constant cells with fractional derivatives than the integer order derivative. We know that investigations with different fractional order derivatives suggest that they have relatively little impact on general properties of the constant invasion system. Fractional derivative equips the distant sequence of constant cells type 1 and 2, migration towards the normal cell domain. Similar pattern change also observed in the evolution of normal cells density U3, and acidification concentration change also observed in the evolution of normal cells density U3 and acidification concentration U4 due to the influence of fractional derivative. Further, the influence of fractional derivative with different values of alpha compared with alpha equals 1. Discussed along the line y equals x. Numerical results are depicted in figure 3 to 6 at time t equals 10, 5, 10, and 15, and 20. From these figures, it's clear that density of constant cells, both type 1 and 2, increase in when alpha decreases. At the same instance, acidification concentration due to H plus ions, fractional derivative increase, U4 increases when alpha decreases. By comparing all these numerical results, we understand that fractional derivatives increase the population of constant cells at some position of the domain. Therefore, by comparing all the simulation results in figure 1 to 6, it is not difficult to find that fractional derivative change in the invasion of constant cells towards normal cells by comparing with integer order derivatives. Therefore, we conclude that the proposed computational model can be employed to forecast the location and shape of the tumor at a particular instance during constant growth and invasion. And this is the list of the main references of this work. Thank you very much for your attention. I wish you all happy Friday.
شكرا لك. وفي الختام شكرا على حضوركم وعلى حسن الإصغاء والمتابعة. الكل يتقدم لالتقاط صورة تذكارية ويليها حفل صغير يشرفنا حضوركم.
لا البنات وقفهم هنا بزاف. يوسف وقفهم قدام الطابلة من تحت. طيار الفحلة غير ربي من تما.